Hi, everyone. I'm happy to be here today to present our work, NetVigil, Robust and Low-Cost Anomaly Detection for East-West Data Center Security. This is work done in collaboration with my wonderful colleagues from Microsoft, Princeton, and Rice. So today, data breaches continue to plague large organizations across the globe. A single data breach can cause upwards of millions of dollars in damages due to the destruction, alteration, and extraction of important data and intellectual property. Unfortunately, today, it's very difficult to detect these data breaches in practice. So to better understand why it's so difficult to detect these data breaches, let's look at an example scenario. Here we have a data center network we want to secure, and data is sent back and forth with external users. We call all network traffic that enters or exits the data center as north-south traffic. And a lot of security solutions today are deployed at the network perimeter. And while these security solutions perform fairly well in practice, we observe that they're ill-equipped for detecting threats within east-west traffic, which is network traffic that flows within the data center network. And this is problematic because an attacker may circumvent the firewall, and once they've infiltrated the network, they can propagate to other machines, and they can mount additional attacks. So why is securing east-west traffic so challenging? The first challenge is that east-west traffic is very high volume. Indeed, we see that from existing studies. East-west traffic volume is about 4.5 times higher than north-south traffic. Additionally, a lot of existing intrusion detection systems, or IDSs, require processing every single packet, and this is extremely compute intensive. Indeed, we see from existing IDSs, we require many hundreds of compute cores just to secure a single 100 Gbps link, which can be extremely costly. The second challenge that we see is network dynamism. Over time, the network can change significantly. So nodes can increase or decrease the amount of data that they send and receive, and nodes can change who they talk to over time. And because of this dynamism, data-driven IDSs struggle and may incur very high false positives. And these false positives are bad because it results in a waste of resources and time when people have to look into the causes of these false alarms. And additionally, these false alarms really erode trust in the security systems. And indeed, we see that for some existing state-of-the-art IDSs, we can expect to see up to 47% false positive rates for more complex attacks. So one thing we observe is that although a lot of these prior IDSs use packet processing, not all packet data is actually necessary for intrusion detection. For example, a lot of packet payloads aren't used because they're encrypted. Thus, we see an opportunity in which we can leverage flow-level logs to detect threats. And flow-level logs are essentially condensed flow-level connection summaries, and they can save significant operational costs because they're much more compact compared to packet-level traces. Here on the bottom, we have an example of a flow log entry. Here for each flow, we have aggregate statistics or features, such as number of packets and bytes being sent and received. And we note that flow logging is supported by a number of popular cloud providers, such as Azure and AWS, all at low costs and at low overheads. However, naturally, one problem that we see is that flow logs have very limited information. And indeed, we see that when we naively adapt existing state-of-the-art IDSs to flow logs, we can incur significant reductions in performance across a number of different attacks. So in building an effective east-west security system, there were several design goals we try to keep in mind. The first design goal is we want to scale to high volumes of east-west traffic at low cost. The second design goal is that we want to adapt to the dynamism within the network in order to minimize false alarms. And going forward, we make this key observation that although the network communication patterns may be complex, they're not entirely random. In fact, each node within the network plays a key role in a larger service or application. Thus, instead of just considering each node's communication patterns in isolation, but also considering the contextual information of other neighboring nodes, we can thus make network behavior much more predictable and learnable. So going forward, we leverage graph abstractions, in which we leverage graphs to holistically and efficiently model all of the network communication patterns. And these graphs can then be ingested by downstream models. So this leads us to our approach that we call NetVigil. In NetVigil, every node in the network gathers flow level logs. These flow logs are then aggregated. And a feature extractor takes these aggregated flow logs and constructs a communication graph. This graph represents all the communications that are going on within the data center. This communication graph is then ingested by a graph neural network, or GNN. And the GNN tells us which one of these connections are anomalous and which aren't. The anomalous connections are then forwarded to a security team for further investigation. Now, connecting back to our design goals, we really want to build an anomaly detection system that is low cost and also robust to changes in the network. So let's first tackle this challenge in how we detect anomalies at low cost. A key component of our pipeline is feature extraction. And the first question for building a robust feature extractor is, at what granularity should we construct the graph set? There are prior approaches that do construct graphs based off of network data. However, a lot of them construct what we call flow graphs, in which each vertex in the graph represents an IP and a port. However, as you can see on the right, this results in a very large and expensive graph. For a network consisting of 300 nodes, we get a graph that has 139,000 vertices and 115,000 edges. So instead, we model graphs at the granularity of IP addresses, in which each vertex instead models a single IP. And in doing so, we get significant graph size reductions. And we get a graph that's instead 300 vertices and 10 to 20,000 edges. And as I'll explain in the next slide, we're able to do this while still retaining port data. So the second question we look towards is, what edge features do we use to represent the communication patterns? So to answer this question, we did an analysis of existing attacks. And we tried to determine what information do we need to extract from our flow logs to detect various threats inside of the network. And we came up with a number of important features. One example is the number of transmitted packets or bytes, which can be very important for detecting volumetric attacks that involve sending a lot of data from one node to another. Another example is the number of ports, which can help us identify various forms of network reconnaissance, such as a malicious actor trying to determine which ports on a victim machine are open or closed. And in summary, by using flow log processing along with efficient graph construction, we can lower compute costs significantly. So the second challenge we attempt to tackle is, how do we build a GNN that is robust to the dynamism of the network? So recall from before that the reason why we use graphs is because they holistically model all the network communications, and they also allow downstream models to learn those patterns. So for realism, we assume that labeled data sets are unavailable, and so we thus employ an autoencoder architecture. This autoencoder architecture is comprised of two components, a GNN encoder and a GNN decoder. First, we take the edges from the input graph, and they're given to the encoder. The encoder then constructs what we call edge embeddings, which are basically representations of the graph edges in a lower dimensionality. The GNN decoder then takes in as input these edge embeddings and attempts to reconstruct the original graph edges. And we compute what we call this reconstruction L1 loss to help us to determine how similar our reconstructed edges are to the original graph edges. And this reconstruction loss also helps us to gauge how well our GNN is doing in learning the complexities of the communication patterns within the network. So to get our GNN to be robust in practice, there were two additional features we had to implement. The first addition is data augmentation. So we note that through data augmentation, we can artificially add additional training samples to our training set to improve dataset heterogeneity. And the way we do this is we add various perturbations to the graphs, such as removing edges and nodes, adding noise to edge features, and removing non-application edges. And on top of this, we add what we call a contrastive loss, which enforces that augmented versions of an edge be similar to each other. Secondly, we leverage temporal dynamics. So to further improve generalization of our model, we train on multiple graph snapshots over time. And we make an observation that networks typically have substantial temporal stability. In other words, when changes in the network occur, they typically occur gradually over time rather than abruptly and all at once. So we codify this observation in what we call a temporal loss, in which we enforce the same edge in two consecutive time steps to be similar to each other. So in summary, by leveraging both temporal and contrastive learning, we can make NetVigil much more robust to network dynamism. So putting it all together, during training, our feature extractor takes in as input all the flow logs from the network, and it constructs a graph. Graphs are then given to our data augmentation engine, which generates additional versions of these graphs with various perturbations. The GNN encoder takes in these graphs and produces edge embeddings. And we then compute our contrastive loss and temporal loss. These edge embeddings are then given to a GNN decoder, which then tries to reconstruct the original graph edges. And using these reconstructed edges, we compute this reconstruction L1 loss. And during training, this reconstruction loss, contrastive loss, and temporal loss are used to update the model's parameters. During inference, we exclude data augmentation, contrastive loss, and temporal loss, and instead we perform anomaly thresholding on the reconstruction loss to determine which connections are malicious and which are benign. The malicious connections are forwarded to security team for further investigation. So for evaluation, we create and release the first open source east-west security dataset. And this is done by taking a 16 VM deployment and running a microservice application on top of it. We then mounted a number of different attacks that are representative of existing attacks in the wild. So for example, we run Infection Monkey, which simulates various attack scenarios by doing things like network scanning, exploiting various services in the network, and propagating to other nodes. Another example attack is DNS amplification, in which we take several compromised nodes and we use them to send DNS requests to a DNS server and direct the responses to a victim. And in total, we support 13 total attacks that span varying levels of complexity. For our evaluation, we look at a number of key questions. So we look at the performance of NetVigil on multiple different attacks. We look at the detection latencies. And we also compare operational costs of NetVigil compared to state-of-the-art baselines. And all of our experiments compare NetVigil against two baselines that we call Kitsune and Whisper. So for our performance evaluation, we primarily look at area under the ROC curve, or AUC. And this value helps to capture how well the model can perform in distinguishing between different classes. This value compares the true positive rate and false positive rate at varying thresholds. And this is done by plotting what we call an ROC curve, which you can see on the left. And using this ROC curve, we compute the area underneath it, and we get our AUC value. This ROC curve gives us an AUC of 0.5. Here's an example of a better AUC of 0.96. So overall, we see we can get significant improvements in AUC. We see average AUC improvements of about 0.22 over existing baselines. And we also see an average false positive rate improvement of 1.8 to 2.9x over these baselines. And these wins largely come from both our novel feature extractor as well as our graph representation learning. Secondly, we look at the detection latencies of NetVigil, and we see that we can reap significant wins and speedups compared to these baselines. And a lot of these wins largely come from using flow-level logs, which, as I mentioned before, are much more condensed and compact compared to packet-level traces, which results in much less data that NetVigil has to process compared to these packet processing baselines. And lastly, we compare operational costs, and we can see that we're able to reduce costs by 2 to 16x by lowering both storage and compute overheads. And similar to the last slide, we're able to get these operational cost wins largely by using flow logs and reducing the amount of compute servers that we have to purchase. We note that in using flow logging, there is an additional costs that we have to undergo for the logger, but these are quite small comparative to the compute costs. We also compute operational costs across our production trace at Microsoft, consisting of about 400 VMs. And we can see that our operational cost reductions are much more pronounced in this scenario. This is because in this production trace, each TCP flow had many more packets on average, which resulted in much higher overheads for Whisper, which processes every packet. And additionally, this production trace had a much higher percentage of TCP flows, which resulted in further condensed flow logs. So in conclusion, I talked about why securing east-west traffic is difficult due to compute complexity. We introduced NetVigil, which is a low-cost anomaly detection system. It uses cheap flow logs and graph-based inference. We also showed how NetVigil can yield significant wins in AUC over existing baselines, all while reducing operational costs. And we also create the first east-west security dataset. And lastly, efforts are currently being made to integrate NetVigil into production teams over at Microsoft. Thank you all for listening. Please let me know if you have any questions.